Today's distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Bo Chen, Associate Professor in the Department of Computer Science, Michigan Technology University. The title for today's talk is Enabling Data Recovery from Ransomware Attacks in Mobile Devices. Dr. Chen leads the MTU Security and Privacy Lab at an MTU ICC Center for Cybersecurity. He also serves as MTU Point of Contact for NSA National Centers of Academic Excellence in both cyber research and cyber defense. He's a Fellow of EAI, a Senior Member of ACM, and Senior Member of IEEE. His research focuses on cybersecurity with a particular emphasis on embedded systems, security, Internet of Things, CPS security, and cloud computing security. He has received the 2024 MTU Rath Research Award, 2020 MTU Research Excellence Fund Award, and 4 Best Paper Awards at EAI SmartSP 2024, EAI AC3 2021, ACSAC 2017, ACM CODASPY 2013. He has served on the various program committees for over 80 academic conferences, including IEEE S&P, ACM CCS, ACSAC, IEEE IFIP DSN, ACM AsiaCCS, and ESORICS, and received Outstanding Program Committee Member Award from ACSAC 2024. His research and education initiatives in cybersecurity has secured $5 million in external funding since 2019, including $1.1 million from National Science Foundation as principal investigator. Dr. Chen, it's a great honor to have you as part of the webinar series at UND. Thank you so much for taking the time this morning with us. And the floor is yours, and you can share your screen.
Sure. Thanks for introduction, Prakash. Let me share my screen. Can you see the screen?
Yes.
Sharing? Okay, that's great.
Cool.
So so today I'm going to share some of the word about ransomware defense. We have been working on ransomware for I think 7 years. So will I share some of the results, something maybe useful to your future research or even in a future study. So let me start from some background because I want to defend against ransomware in mobile device. A very important actually storage hardware for any mobile device is for flash memory storage. So I think you can also see this flash memory in other, for example, solid state drive, right? In laptop, desktop servers, right? Use SSD a lot today. Especially for mobile device, IoT device, we use some flash memory card, for example, eMMC card, SD card, mini SD card, or micro SD card, and so on and so forth. And even if you use, for example, portable storage, right, you may use USB drive or some other things, right? All of them use flash memory. Mostly flash memory used very broadly in today's storage, especially for embedded systems. And now let me slightly introduce about how can we write and read flash. I think I need to go back one slide. Oh, okay. So introduce a bit about flash memory, right? So we know that there's a lot of types of flash memory, but 2 major types. One is NAND flash, another non-flash. But mostly, I will going to focus on today's the first is NAND flash, okay? Because it used a lot in the storage system for mobile device or embedded systems. And for NAND flash, I think I give the architecture here, right? So you can see that the entire flash here is divided into something called blocks. Block mostly is something big, is around 100 kilobytes, okay? And also the block actually further divided into pages, okay? So why we divide into block and pages? Because when we try to read and write flash memory, usually it's in terms of pages. But if you want to, for example, do an eraser, usually it's performed in terms of blocks, okay? And now let's see if I want to program flash memory, how can I program that? Okay, so program flash memory is different from hard drive. Why is different? Let me show you following. So initially all the bits in flash memory is all 1. Okay, that's the initial state. But what if I want to, for example, write a byte? This byte is 0B, right? So the rule here is that the big 1 can be programmed to 0. But unfortunately, the reverse operation is undoable. You cannot program 0 to 1. You can see it's completely different from hard drive programming. Okay, so 0 can be tuned into 1 except doing a eraser. Okay, but now if I want to write this 0B, what can I do? Right? We know that 0B is 8 bits, right? 4 leading 0 and 1 0 1 1, right? So you can simply convert 1 to 0 here, right? 1 0 1 0 here, 1 0 here, and here, right? This one, oh, I think the display something is wrong here. 1 0 1 0 here, 1 1 1 0 1 1. Okay, so but unfortunately, if I want to modify this EOB to another byte, for example, EOF, which is 0000111, can I do it? Right? So you can see that based on the rule, unfortunately, I cannot do it. Why? Because that means that I need to convert 0 to 1. But according to the rule, right here, 0 cannot be programmed to 1. That means that I cannot simply modify 0B to 0F. Okay, it's undoable. Then if really I want to modify this, what can I do? One option is to, we will first do a laser and go this by, we're going to come back to O1. And from O1, I actually can program to this 0F. Okay, you can see that doing override actually is very difficult compared to traditional hard drive. Okay, because these are fundamental different programming mechanism here. Okay. And now, because these special things like there's few special characteristics for flash memory, basically there's two major special characteristics. First is called update unfriendly, right? Maybe you already got something from my previous example, right? If I want to override something in flash memory, it's very hard, it's very difficult. Okay, so slightly I introduced a bit previously, right? If I want to write something to flash memory, the unit is in terms of pages. But if I want to do eraser, the unit is in blocks. Okay, so now, for example, if I want to override something of these pages, right, these yellow pages, what can I do, right? I cannot simply override that because the rule I just saw. Okay, what you can do is that first I need to do I need to copy other data. Okay, and then I'm going to do a block eraser, just that I can erase the entire block because I just say that eraser is performed only on blocks, a big block. Okay. And after that, I'm going to write this data back. You can see that to override or update 1 pages, I need to read and write 3 pages, right? This actually is expensive, right? It's a big write amplification here. Okay, so that's why is that flash memory is update unfriendly, right? So that's why typically when we do flash memory writing, we only do something called out place update, okay, rather than in place update. And the reason I just explained why. Another special characteristic of flash memory is that unlike traditional hard drive, okay, traditional hard disk, you can keep writing again and again, right? Unfortunately for flash memory, you cannot writing too much on the same place, okay? So each flash memory block typically only allowed to program erase for limited numbers of times, for example, 10,000 times, okay? That means that after 10,000 times, those flash block or flash pages may be just run out. It cannot use to store data anymore. Okay, that's why typically in flash memory they have a mechanism is called real leveling, such that when you write data to flash memory, you need to somehow make sure that the data is right somehow evenly across the entire flash, right? Just make sure that a single page will not be run out in a short time. Okay, so there's two very special characteristics of flash memory, but definitely we're gonna have other more. But I'm focused on that. Let's just focus on these two specific for this topic. Okay. And because flash memory have some special characteristics, right? I just showed that. That means that if I want to manage flash memory, I cannot simply use traditional file system, right? I cannot use ext, ext4. I cannot use FAT. That's only designed for the traditional hard drive, hard disk. Okay. Really, flash memory needs something special. We need flash specific file system. Okay, for example, you need to use YAS2, right? Or you can use JFFS or JFF2 or UBIFS. That's actually a unit file system specific design for flash memory. Okay, another option you can do is that this just like a lot of your SSD doing today. Okay, we know that SSD have the same interface as the traditional hard disk drive, okay? Because they maintain the same broad access interface. But inside different. Inside they have something called flash translation layer, okay? And what's flash translation layer? It's just a flash firmware which embedded into the flash storage device such that they can handle those unique special characteristics of flash memory internally, such that, right, from the outside you don't need to know the difference, okay? The outside is simply equal to a hard disk, okay? But the inside is handled by this flash translation layer, okay? Other things like USB, SD card, MMC card all have FTL built inside, okay? And this is most popular for today's flash storage device. And let me give a little bit detail in flash translation layer, right? We just talk about flash translation layer is a special firmware layer inside into flash storage device, okay? So you can see that the flash translation layer actually is here stay between the file system and the actual flash memory, okay? Such that you can use provide a unit broad access interface to the external party, just like right, just like traditional hard disk drive, right? Just like traditional broad device, okay? And flash translation layer typically provide a few unique functionality, okay? First is called address translation layer, because I just talked about that, right? The external interface is broad-based access interface, just like hard disk, right? That means that, but inside we know that there's broad, there's pages, right? That means that the address is completely different. You need to do a translation between these two types of address, okay? And second is something called garbage collection. We just talked about flash memory use output update, which means that you don't actually delete the data, right? You only rewrite the data to a new place, but you just invalidate the old data. But the space which store the old data should be reclaimed over time, right? That's why I need some sort of garbage collection, okay? It's GC. And variant, I just already introduced variant, right? Make sure that you're not going to wear out flash pages too soon, right? You need to make sure that the data writing to flash should be distributed evenly across the entire flash. That's why variant is needed. And also background management, right? We just talked about, right? Flash memory or flash pages can only allow you to programming a limited number of times, okay? But over time, right, it's unavoidably some of the flash pages may be worn out, okay? And you need to manage those bad pages, or more specifically those bad blocks, okay, which consists of pages, okay? You have the bad block management, which is also needed, okay? I guess now I'd like to give you some high-level background for flash memory, which is very important for any mobile device or embedded systems. Now, let's come back to our focus today is to defend against ransomware, right? I think every people here at least heard ransomware before. It is very popular today, right? It's actually a very major attack today, right? So you can see a lot of ransomware samples of variants available, right? It compromises a lot of data, right? Ask for the ransom money of that, right? So this actually the news actually just copy here, right? So some Black Seal ransomware and County ransomware, or those color code ransomware. There's a lot of ransomware, okay, today. And ransomware, you may ask, what's ransomware, right? So you know that typically ransomware mostly is just a malware. But this malware is slightly different. It's a special malware, okay? This malware, special malware, the purpose of this malware is to try to retrieve the access of the victim's data, okay? Such that if you want to get the access of the data, you need to pay the ransom, okay? So you can see that it's a malware. Unfortunately, it's a special malware which is just designed for ransom purpose, okay? And to ransom, to get a ransom, the malware need to somehow retrieve the access to the victim's data, okay? And we can see that, right, ransomware definitely very bad, right? It actually is a few bad things actually caused by ransomware, right? First, definitely is financial loss, right? I think according to some report in 2023, the average cost of one ransomware attack is around 5 million. Okay, this is a lot, right? And also another bad thing is operation disruption, right? You can see that if the data is compromised by ransomware, right, it's become inaccessible, right, to the victim. If you're running business, right, definitely the business will be interrupted, right? Definitely, right? It's a bad thing. And then reputation. think about that. If my data is compromised by ransomware, right, it's very bad for my reputation. This indicates that I have not well protected the data, right? It gives very bad imagery to your customers. Okay. Last thing definitely is going to have something from legal or regulatory consequence. Think about we have a lot of regulation, GDPR, HIPAA, right? If your data compromised, that implies that you are not complying with those regulations, right? You're going to have some legal issue potentially. Okay. And because ransomware is bad, right? Definitely, that's why a lot of federal agency, they collaborate to try to defend against ransomware. One typical example is something called stopransomware.gov. Okay, so this actually is a joint effort between CISA from Department of Homeland Security, FBI, and NSA, right? They launched this initiative, okay, to stop ransomware and then provide a lot of resources, guidance, recommendation to help people or help enterprise to mitigate the ransomware attack. Okay, so but my focus mostly doing research, try to address those fundamental problems in ransomware defense. Okay. And then let me start from briefly introduce the major type ransomware. There's two major types. One is something called local, another is called crypto ransomware. Okay, so local ransomware mostly is nothing means that you're going to lock the system and then ask for ransom. That means that if you want to get access to a system, you need to pay. Okay, another crypto ransomware, which means that you're going to encrypt the system or encrypt the files, the data, right? And if you want to decrypt, you need to pay. Okay, so clearly for local ransomware, it's not difficult to be defend again, right? It's to defend again because only lock the system, but the data are there, right? So we can simply remove the stored media, for example, the SSD drive or the flash memory card, right? And then use the stored media in another new computing device and copy our data. That's it, right? It's simple because the data is still there, right? But what about the crypto ransomware is now it's hard, right? Why? Because the data is already encrypted, right? And to get the data, first option you can decrypt data. But how can I decrypt data, right? First, I can pay. I pay the ransom and then get back the key and then decrypt that. But definitely it's not a good solution. Why? Because, right? So first, even after I pay that, it's not guaranteed that I'm gonna get back the key, right? A lot of reports shows that even though after the victim pay, they not get back the key because, for example, the software built by the ransomware attacker is poor. They don't even correctly store the key or something like this, right? So, and also there's no customer service, right, from the ransomware attacker. So it's hard to guarantee that after I pay, I can ensure my data, my key can come back, okay? So another solution I can do is that depends on what type of encryption the ransomware was using, okay? If the ransomware is using something called symmetric encryption, it's potentially to get a key locally. Why? Because when the ransomware try to encrypt the data, they need to use the symmetric key at that time in the victim device. That's why there's some word shows that potentially I can extract the key, which was in the victim computer before. Okay, but it's unreliable. Okay, it's hard to give a 100% guarantee the key can be extracted here. Okay, so the first option is just get the key, and the second option I can do detection. It's ransomware detection. That idea here is that I need to detect ransomware and block it as soon as possible before it can encrypt more data. Okay, so important thing here is that the detection need to be very fast. Okay, so but another disadvantage for this option is that even you can detect it, that means that before you can detect it, there's some amount of data already be encrypted. Okay, this part of data still will be lost. Okay, so that means that option 2 may not be optimal. Okay, and then the last option I will focus today is called secure data recovery, which means that I will going to ensure the compromised data is always recoverable after the attacks. But how can I provide this assurance? Okay, that's something I'm going to talk more next. So the key idea is what? The key idea is that the data actually was there in the victim computer before ransomware corrupt them. That means what? That means that if there's a way right? We can actually, we it's likely to get back those data by doing, for example, forensics, right? Because the data was there before. That means that there's some data remnants in the memory, there's some data remnants in the processor cache, right? Something like that. If I can extract those data from those places, likely I can get back some of the data. Okay, but we know that no matter if memory or the processor cache is actually volatile, right? Which means that they may be lost if power is lost, right? And also because the memory and processor cache is highly dynamic, right? That also makes that it's hard, right? It's very, very less reliable to extract data from those places, okay? And my focus is slightly different. Actually, I try to extract data from the local disk, from the external storage, okay? And what we rely on actually is to the unique hardware nature of flash memory to make sure that data can be extracted from the local disk, okay? And how can I do it? I will introduce more later. So before that, let me review a bit about the special nature of flash memory. Okay, so I just talked about outplace update, right? Let me give you a concrete example. So how exactly this outplace update happens here. Okay, and to better present this, I provide two cases side by side. One is to do update on the mechanical disk, or another to update on the flash memory. Okay, and on traditional mechanical disk is do in-place update, but in flash memory we're going to do out-place update. And what the difference here, right? I'm going to show you. For example, already I stored data A, right? I write data A, and then it's going to store in the hard disk here. Also, in flash memory, I write data A, and actually flash install in the flash pages here. Okay, now I want to do a update, right? So let me do simultaneously, right? Let me first doing for mechanical disk this. Now I want to override A with, for example, B. You can see, right? On the file system, B, we're going to replace A, right? And also in the actually storage hardware, or specifically in the sector, disk sector, right? You can see B, you're going to override A here. This is in-place update. This means that B is completely override A, right? Unfortunately, for flash, you can see the difference here. Now I also want to override A with B. Let me see. Now on the file system, B, you're going to override A. But in flash memory, you can see what's happening here. Because in flash, I just showed that it's hard to actually override in flash pages. You need to do outplace update, which means that I'm going to find new location store B, a new flash pages here, right? But A is still there. Okay, it's just invalidated. Okay, it's not actually deleted. It's just invalidated. Okay, now actually I think you got hints, right? If the ransomware actually try to corrupt data A, right, and then what I need to do is to recover data A, right? But A actually is still there in the inside flash memory. Okay, this actually gives you a hint, right? Why it's possible to extract the data to recover the compromised A here, right? So this is the fundamental idea. Hopefully you get something here. And before that, before I specifically introduce how exactly we can recover, right, the data compromised by crypto ransomware, let me summarize a bit about those typical behavior of crypto ransomware. We know that crypto ransomware actually very, very diverse. Okay, they may do a lot of different behavior. However, there are two major behavior which is typical or mostly happen for typical ransomware. Okay, the first behavior is that the ransomware, we're going to encrypt the victim data and then replace the victim data on this. Use those ciphertexts. Okay, so that's the first behavior. The second behavior is that the ransomware, we're going to encrypt the victim data, but write a ciphertext to the disk in a new location, and then delete the victim data. That's two typical behavior. Okay, and then I go to show next how we can get data recover in these two behavior. Okay. So for first behavior, right? So I want to recover data compromised by ransomware. Let me show it step by step. Okay, so we can see that we have both system I/O and ransomware I/O. Okay, and then also what exactly happening in the storage device here. Okay, so you can see first the system write A and B. Okay, write A and write B. That's the system I/O. It's not from ransomware. Okay, We can see that A, we're going to store in the flash pages here, B, we're going to store in flash pages here, okay? And now we have ransomware, right? Ransomware comes here at this point, T0. And ransomware definitely try to compromise data, right? To compromise A and B, ransomware need to first read A and B, right? And next, the ransomware is going to encrypt A to A pi, and then override A with A pi, and see what's exactly happening, right? I think I got a question here.
We can deal the questions after the session.
Sure,
if you
let
want.
me just put it here. So after we encrypt A to A pi, right? I need to the ransomware need to override A with A pi, right? You can see what's exactly happening in the disk, right? So now you can see A, we're going to override A pi here, and then because our place update, right? A pi need to store in a new pages here, okay? And then the old A, we're going to invalidate, okay? But still there, okay? And similarly, right, we're going to encrypt B to B pi and then override B with B pi, right? You can see that, right? B is override B pi here, but in the actual flash memory, B pi is going to in a new pages, okay? But now you can see that, right? Clearly here, A and B can be extracted later after ransomware attack to recover the compromised A and B, right? So this shows you that how we can recover the data in the first case, okay? So for second case, right? So the ransomware, we're going to delete the data and then write the cipher to a new place, okay? Let's see step by step, right? What's happening here? Similarly, right? Write A and B. And now ransomware comes at type 0 to T0. What's happening? Ransomware going to encrypt A to A pi and then write A pi, right? A pi is going to write to a new place. Definitely going to eventually store in a new pages. Now, the ransomware try to delete A. That means that ransomware is going to perform a system call here to delete A here. But you know that, right? Unfortunately, even though you perform a deletion on the file system, but there's no deletion inside flash memory, okay? It's not going to do actual delete for you, okay? Only things that can only invalidate A here, okay? There's no actual deletion happening inside flash memory, okay? And similarly for B, something similar, right? Include B to B pi, write B pi, right? And then B pi is going to store in flash pages here, and then delete B, also similar to A, right? There's no way to actually delete B inside flash memory, only invalidate here. Okay, you can see in both cases, right? I can also extract A and B. In this case, I can extract A and B and then restore the compromised data for these cases, right? I think for now, you can see that how we can ensure recovery of data in both typical cases for ransomware. Okay, but is that's it? No, there's a lot of other things we need to consider. Okay. So I just talk about that, right? For both cases, right? The temporary preserved data can be extracted to restore data after ransomware attacks, right? And those old data just invalidate by the flash translation layer, okay? And that means that after invalidate, they are invisible to OS, okay? But they can be extracted later, okay? But you may ask, so can a ransomware directly corrupt those old data, right? We just say that it preserved in flash memory inside, right? Can the ransomware just go there to corrupt them? The answer, unfortunately, is no, right? Because why? You can see that this is a USB device, right? There's inside chip is flash memory chip here, right? The flash memory is completely isolated from the other parts of the OS, right? So that means that inside this flash storage device, we're going to have independent processor RAM, right? And also we have independent flash firmware. We only provide very limited access interface, for example, SCSI, ATA, USB, right? That means that the OS from outside, there's no way to hack into that and then compromise data outside, inside, okay? It's just not possible based on this limited access interface here, okay? Because everything here, hardware, software, is isolated from the OS, okay? That implies that even OS is compromised by ransomware. There's no way for ransomware to corrupt the data, all data preserved inside, okay? But this old data still may be reclaimed. Why? I just introduced garbage collection when I talk about background for flash memory. Garbage collection is built inside flash translation layer. That means that periodically you're going to recreate those invalid data. right? So if the data is invalidated by the ransomware, although they are temporarily preserved, but they may be declared by garbage collection. Okay, that means that if you want to ensure data recovery after ransomware attacks, you need to make sure that, right, the garbage collection should not recreate those data. That's why we need a new garbage collection strategy. I call this phase garbage collection strategy. How this works? This works as follows. Okay, so if there's no ransomware, this garbage collection just works as regularly. However, if there's ransomware, the garbage collection, we're going to do something specially. Okay, it will temporarily disable if there's any ransomware. Okay, but to enable this strategy, we need something. We need to know whether there's ransomware or not, right? That's why I need a ransomware detector. Okay, and how can I build this ransomware detector? Is the next question I'm going to answer. So we know that we can use a system level or user level ransomware detector. However, this is not secure, right? For example, if the a ransomware compromised OS, right? Those user level, system level ransomware detector will not work, okay? They will going to compromise also, okay? And then our solution try to see whether it's possible to detect ransomware in the inside flash storage, which is in the flash translation layer. And is there, but the question is that, is this type of FTL-based malware detector possible to design, right? Is feasible or not feasible, right? So that's next question I'm going to discuss. And to answer this question, we collect a few, more than 500 ransomware samples from 11 families, okay? And then we use half samples to try to learn the access pattern. Then we learn those ransomware and what happened inside the flash memory, or what is the access on the flash translation layer. Okay, and then we collect those access inside flash memory and try to understand whether they have any pattern if the ransomware is running. Okay, unfortunately, we do find out there are some patterns after running all those test samples. Okay, you observe 4 types of access patterns, right? So here R means read, W means write. You can see that, right? The first type A, is that this is the I/O actually happen inside the flash storage. You can see the read happen in this location with that many of bytes have been read. And after that, we can see write also happen in the same location. With almost the same length of write. Okay, we can see this also, right? The same location, read and write are almost the same length. Okay, so this is the first type. You can see that, right? That means that after ransomware read the location with some length, they're going to write the same location with the same length or approximately the same length. The first time. The second time, you can observe also here, right? The ransomware actually read this location and with this length. And after that, we're going to write this location, almost this location with slight different length, but it's smaller than this length. Okay, similarly happen here. This and this, right? This and this. You can see, right? The read write location is almost the same, but the size of write is slightly smaller than the size of read. That's why the reason is that likely the ransomware, after they encrypt data, they're going to do completion before the write. Okay, that's why the write size potentially slightly less than the read size. Okay, and another pattern we observe is that the ransomware write some location with some length, and then read some location with some length, and then write another location but with the same length. Okay, similarly happen here, right? This location, write that many bytes, and then write this location, slightly but very similar bytes. Okay, so this is the type C, which means that the ransomware first write someplace and then encrypt data. No, first read someplace and then encrypt data and then write to a new location. But the size of the read and write is very, very close. Okay. And the last pattern we observe from the our experiments that you can see that the read and write has some repetitive pattern. Here you can see ransomware write 64 bytes and then read 64 bytes and then write AAA, something like this. Or here write 42 bytes and then write AAA, something like this. Right, this read and write has some pattern. Mostly, I think this comes from the encryption algorithm. The ransomware likely they divide the data into a group and then do encryption and summarize them. Right. That's why you can observe this read 64 bytes and then write AAA read 42 bytes and then write AAA summarize this. Okay. But regardless, you can see that there's some pattern. Okay, if the ransomware is running in the victim systems. And then based on this pattern, that means that it's potentially to detect ransomware inside flash translation layer. Okay. And now let me briefly talk about some implementation we have done, right? So we actually implement those design into an open source flash controller. Okay, it's called OpenFM. And we also pour our prototype to some embedded systems. Okay, our PCH3131. Okay. And then let me show briefly some results. Okay, here this result actually shows some detection effectiveness. You can see that I first define something called threshold, which means it's the percentage of type A, B, C, or D access compared to all access. You can see this is this sample here within this rectangle is all ransomware. Okay, you can see the threshold here mostly is more than 0.8. But however, for regular software, you can see this threshold mostly is more than 0.5. Okay, that means that there's clear difference between the ransomware and the regular software. If I put a threshold, for example, around here, right, you can see I can clearly differentiate these two types of, right, the ransomware and the regular software here. Okay. And our result shows that for type A, B, C ransomware, if the threshold is choose between 0.55 and 0.78, the false positive rate and false negative rate also is very small. Okay, and similarly for type D ransomware, the threshold choose between 0.63 and 0.87. Both for positive rate and for negative rate will be also very small. Okay, this actually justify the effectiveness of our design, which detect ransomware inside the flash storage. Okay, this is in the flash translation layer. And how about the efficiency? Okay, so here we want to restore around 500 megabyte data. Okay, because that's the size of this embedded system. You can see that all the types are altogether, right? Almost is around 4 seconds. We can restore 500 megabyte data. Okay, that means that it's very efficient. Okay. And then we also evaluate a bit about how our design impact the regular flash block device. That means that because we need to do additional operation besides the regular flash storage system, right? What's the additional overhead, right? You can see compared to the original flash controller, this is our something after incorporate our design. You can see like we accept different read line patterns, including sequential read, random read, sequential write, random write, right? For all those patterns, we can see our design definitely slightly decrease the throughput, right? But the decrease here is not a lot. It's around 10 to 20%. Okay, it slightly affect the regular system, but not a lot. Okay, it also shows that the design is good. Okay. So I guess already go through some of typical design we have been done by for ransomware. But any problem in the design, right? So maybe you already observed that because the thing here is that we need to incorporate a ransomware detection inside the flash translation layer. We do know that ransomware detection, no matter how good it is, right, it's based on AI, right? Unavoidably, it may suffer from false positive, false negative, right? All those things, right? For false positive is fine because it's just a miss around, right? But if there's a false negative, that's bad. Why? If I have a false negative, which means that I do not detect the ransomware. If I do not detect that, I'm gonna recreate those old data in the flash pages, right? That means that I'm not going to recover after the ransomware attack because the data has been recreated, right? So how can I make sure that even I have false negative, I can still ensure recovery of data after the ransomware attacks, right? So that's why we try to have a more robust design. And the key idea for this robust design is we incorporate also version control system, a remote version control system, okay? Together with the local data extraction in flash memory. So the idea is that periodically, we're going to commit all those data changes inside the flash memory, such that they can be securely extracted and then commit to a remote version control server. Okay, you may ask, how can I make sure that it's secure? Typically, actually, the solution we use here is leveraging the trusted execution environment. Okay, such that I can securely extract the data even if the OS is compromised. Okay, and then we back up the data securely to the version control server. And then the latest data change, right? That means that I have not backed up them to the remote server, right? Those data actually can be extracted locally from the FTL. Okay, hopefully now you get the idea, right? That's essentially I build version control system across the remote cloud server and the local mobile device, which means that the data changes in the history from Delta 1 up to Delta N-1 is stored correctly in the remote version control server, but the most recent data changes, right, can be stored or extract from the local flash translation layer. Okay, this is equal to a version control system, right, built virtually on between the two here. And by doing this way, right, any version of data is guaranteed to be retrievable, right? Definitely, any data, even compromised by ransomware, is retrievable, okay, or recoverable, right? Even though I don't detect the ransomware on time, okay? So this is the base idea for the more robustness design. So to conclude, right, this, I mean, it's not complicated, right? Mostly it's to incorporate version control system in the remote server with the local flash translation layer data extraction, okay? That's the idea. Another word I want to slightly talk about is something called file-grade recovery from ransomware attack. Okay, so here is the question. Okay, so in the previous word, you can see that, right? So we focus on recover the entire storage actually, right? So but you do know that, right, the column embedded system, especially mobile device, right? The mobile phone, for example, the most recent iPhone 16, have up to 1 terabyte data, 1 terabyte storage, right? So to restore this 1 terabyte storage is still very expensive, right? It takes a lot of time, right? But what if, for some case, right, I want to just restore some important files, right? Such that I can get restoration fastly, right? Rather than wait too much time, right? So the question here is that can I just restore some important individual files entirely, right? Rather than restore the entire data. Okay. So the answer definitely is yes, right? So see, now I want to recover some files, right? So, and to restore the file, which means that I need to restore two things. First is the file metadata. The second is the file content, right? And to restore the file metadata, mostly that come from file system, okay? And also the file metadata store the location of the file content actually, right? So really depends on what type of file system you use, right? That depends on how we can restore the file metadata. Our observation is here, right? If you use, for example, EXE NTFS or EXE2, so most of the metadata file metadata of those deleted files actually is still maintained in the original structure. Okay, so and that means that after the ransomware attack, it's still possible to extract those file metadata from this data structure. Okay, and if you use EXT3 or EXT4, unfortunately, those file metadata, right, the dislocation inside the file metadata has been actually zeroed out by the OS upon deletion. Okay, but fortunately, there's another thing called journal. Okay, the journal actually we're going to keep a lot of those metadata changes, and that means that after the deletion, it's possible to extract those file metadata from the journal. I think now you get the idea, right? That means that to get the file metadata, we can perform file system forensics, okay, to get back those file metadata. Okay, so the idea I think I summarized here, right? So the first step, I need to restore the file metadata. And to restore file metadata, I need to perform file system forensics. okay, such that those file metadata can be recovered after the attacks, okay? But I need to emphasize that this solution is only effective for the low privilege ransomware, not OS ransomware, okay? Because OS ransomware, OS level ransomware has very high privilege. It can actually compromise those file metadata, okay? And then after I extract the file metadata, right, I actually get a location. I get a location of those file content in the disk. And then for each disk location, I can restore those data originally stored on that, okay, by doing FTL extraction, right? I just talked about, introduce a lot, right? How can we extract the data using our place update in flash memory, right? So, but using this here, we can restore those data stored in specific disk location originally, okay? So I think I got another questions, but let me finish the presentation, okay? So we also access the effectiveness. We collect we try to access them over 54 families, ransomware family. Okay, and for each ransomware family, we pick 1 to 2 samples. Okay, so I also provide a list of the family we have conduct experiment here. Okay, you may ask why I just do it for 92 ransomware. It's based on the limitation of the research time actually, because for each one we need to manually do those embedded system read write load the malware, do something. For each one takes a lot of time for each one. That's why it's hard to do a lot. Okay, because those things need to be done manually in the embedded system. So and then you can observe the how good we can recover data. So among all those texting ransomware, we can recover up to 92.5%. And then there's 7% we cannot recover. The reason is that actually we slightly investigate into the reason because those ransomware actually do something slightly different. For example, they erase the data or delete data for a few times. Something we cannot handle actually. We cannot handle 100%. Okay, but still, if 92% probability, we can recover those data from the attacks. Okay, so we are also open source the tools we developed in this web link. Okay, if you are interested, please download the link to test them. And a side product from our project here is a data recovery tool. Okay, the tool is also open source here. This allow you, if for example, if you delete your file accidentally, you can use our tool to recover those files. Okay, so I think it's something is a side product from this project. Okay, so I guess already most the technical part I've done. So so this research is supported by U.S. National Science Foundation in 2 grants. One is from 2019 to 2022, another from 2022 to 2025. Total is around $800,000 project. Okay. So yeah. So let me finish. Let me see how much time I have. Oh, 12 minutes. So before handle the question, let me briefly go through some other thing in Michigan Tech. Okay. So first, I come from MTU Security and Privacy Lab. I lead this lab. So the lab actually we currently right, the lab have student including PhD student, MS student, and undergraduate student. Okay, so if you are interested in joining the lab, please send me email. Right, the lab actually have been received around $5 million support for cybersecurity research and education. And then the lab conduct research in different areas, including cloud computing security, embedded system security, audio security, network security, and also our physical system, smart vehicle security. We have very broad research interests, okay, across those different important contexts. Let me also slightly talk about Center for Cybersecurity. So MTU actually, this center actually include all the faculty working on cybersecurity. Okay, and currently I'm the director of the center, and the center actually is received National Center of academic excellence in both cyber research and cyber defense, CAE-R and CAE-CD. Okay. And then we have 12 faculty, right, from 2 colleges and 5 departments, including college computing and college engineering. 5 departments, including computer science, applied computing, ECE, civil and environment engineering, mechanical and aerospace engineering. Okay, and then we work on very diverse problems, including cyber physical system security, cloud computing security, AI security, hardware security, network security, blockchain, power grid security, and cybersecurity in construction management, and also cybersecurity education. Okay, so feel free to approach to me if you want to collaborate with the center. Okay, I think now I should try to handle those questions.
Thank you. Thank you for a
Sure.
fantastic presentation. I appreciate your time. And
Sure.
we'll take some Q&As, and looks like there are a
Sure.
lot of questions coming in. Hi, this is from Bo Hyun, postdoc fellow at University of Missouri. Thank you for insightful presentation. The question is, if an advanced ransomware encrypts or locks OS-level system configuration files or kernel boot parameters, disabling the FTL-based flash device port interface, what backup strategies would you recommend?
So, so can you repeat a bit about the questions? So, which question is there?
It's a
In the
separate
Q&A or
chat,
not Q&A?
not the Q&A. It's on the
Oh,
chat.
okay, I see. So that's a few
And
things in Q&A and chat. Let me see.
then maybe I can read it for you. Maybe if an advanced ransomware encrypts or locks OS system configuration files or kernel boot parameters, disabling the FTL-based flash device ports, what backup strategies would you recommend?
So actually, I think it's a very great question. I just talked about, right? So really depends on the ransomware's privilege, right? So if we talk about OS level ransomware, it's very strong ransomware, which means that the ransomware has the root privilege. It can actually compromise everything visible to the OS, right? So for this, I think the solution I talk about here is that because FTL, everything is put inside the flash storage, inside the chip, right? That means all those things inside the chip is not compromised, it's invisible to ransomware. The ransomware, even the compromised OS, is not able to compromise anything inside the chip, right? So for our solution there, any OS based ransomware is not able to do anything there. Okay, so so I guess that's one type of ransomware is this OS level ransomware. So that conclusion is that our solution doing data extraction from the FTL is going to work for any OS level ransomware. But another ransomware actually is file system is application level, which means that low privilege. If they have low privilege, that means that it may not be able to compromise those things you mentioned, right? So those OS configuration, all those things, they don't have privilege to do anything. So I guess this will not even be a problem in the case, right? You cannot combine anything, mostly just compromise the files accessible to the ransomware, not the configuration, not those metadata which require high privilege. Okay, so hopefully I think I can clarify your question. And also one more thing, I want to emphasize that we ensure the recovery of data, which means that we preserve this capability. Okay, but how exactly you can extract the data after that, this actually also very depends on how you're going to implement that. Okay, so what I create here is that because this is our place update, and because we change the garbage collection, all those things, make sure that the data before they actually before the after the attack, right? So the data will be preserved there and used for recovery after it. Okay, so I guess I need to emphasize this capability. Okay.
Great, thank you. Let's say the disk is 99% full and then it is infected by ransomware. Would there be enough space for flash drive to create a new storage page for the new data?
So let me slightly reflect a bit about the phase garbage collection. Now you only have 1%, right? Which means that if the ransomware like 0.5%, you know, the ransomware will not going to, I mean, they compromise 0.5%, and then if they keep writing, because very likely we already disable garbage collection if the ransomware detected, right? That no space we're going to declare at this point. So that means that the ransomware is not going to lie anymore if they keep writing, right? Because garbage collection just disabled. And this actually essentially prevent ransomware to keep writing the more data there, right? So that's because we already do something in the garbage collection there, right? So I don't believe that even you have 99% storage system, the already occupied the system still works, okay?
Okay.
Because it's a garbage collection strategy there.
Thank you. Is there any way to evade the file recover? Can you please explain why there was like a 7% failure rate?
Oh, I think I already slightly played that during the presentation. First, I need to emphasize that the solution, because we only build for some sort of ransomware, it cannot guarantee 100% recovery. Okay, if the ransomware, for example, perform very special behavior, for example, they try to write the data a few times again and again, potentially, we may not be recovered. And also because when I talk about the solution, it's only for application level ransomware. Okay, so if the ransomware has more privilege than the application, very likely that will not work. So that's still
What?
potential solution.
Super, thank you. What type of file storage format, exFAT, FAT, do you recommend for PC? Asking your suggestion. What file
What
storage
type file
format?
format? I think
File storage
okay.
format, is it?
First, because I'm working only for ransomware, but I guess when we're testing, it tests different file format. It's, I mean, for the data point of view, it doesn't matter, right? Any data file is fine. For me, mostly it's 0 and 1. Those that's mix. So I don't have a clear suggestions that something you need to use specific format. Any format works here.
Thank you. Is there any particular specific signature pattern that is observed during cryptojacking?
Uh, Cryptojacking.
Yeah, it's a somewhat different question. I don't know why. Do you see any signature pattern that is observed during cryptojacking? Where is the behavioral pattern? What you observed? And
Uh-huh.
here,
So so cryptojack this is a ransomware. It's crypto. Sorry, I
I
don't
don't
get
I
the
don't
last
think
term.
it's an anthem, but I think they're confused with this is a different thing with cryptojacking. Nothing to do with maybe we'll skip that question. Maybe I'm not sure that have you worked with cryptojacking? Maybe have you seen anything in patterns in cryptojacking?
Yeah, I don't think we actually have this sample in my experiment. So that's why I
Okay.
cannot give this answer.
Okay.
Potentially we can
Um,
do it in the future.
uh, what about, you mentioned that during the garbage collection using the CODASPY work, what you did, okay, if there is no ransomware detected, continue to run. But what about stealthy attacks? Do you see, is any chance where the ransomware detector may not even detect that? I'm just curious to see how do we model stealthiness? Have you seen anything new work, or are you looking at any scenarios where we may not even detect that?
First, it may happen, right? I'd say that first negative is unavoidable for any AI-based solution, right? That's why I have a robust design doing incorporate version control system plus the data extraction, right? And then you may ask about any other scenario for. I think there's a lot of scenario because we only access those ransomware we know. There's a lot of attack maybe remain undetected. For example, I can do a virtual attack. I use some virtual machine learning. I know you're a detector, and maybe I use some virtual training such that some behavior such that it's it's always undetectable by your model, right? This virtual machine learning maybe need to incorporate. And some other thing we do know that for example ransomware evolve over time. So the design, for example, 10 years ago may not work because all those algorithms of authentication happen, right? So they incorporate new authentication or it just evolve. So the new ransomware, the detector definitely will not work. This is, I think, a general problem for any malware detector. After 10 years, after 10, 20 years, it still work. They likely not work because the mechanism potential completely change. Now maybe I can use large language model and some other things to do ransomware, but potentially there's no this mechanism before, right? But there's a lot of things. I think that's a very great question. There's a lot of things for ransomware to be explored, I guess, especially the new AI technology, all those things. Yeah.
You had an interesting slide on
Hmm.
showing that y-axis on threshold and zero point 0.5 greater than, something on detecting prob or likelihood of ransomware. How would you come to that conclusion of the threshold level? In what basis, And is it based on the ransomware samples that you tested? What is that zero point 0.5 threshold,
Hmm.
that
So let me maybe go back to that slide to be a little more clear here. I think the slide actually has this. Let me share this again. You can see actually this threshold comes from the sample we access actually. It's not general for anything. So you can see this the sample from 11 ransomware family. You can see that this threshold mostly for them, they have very high threshold. But for other software we testing, which is legal software, you can see that they are threshold here. So you can see a clear difference with these two category, right? So and then typically that's why we think that maybe it's good to have a threshold something between this and this. It's good for this type of ransomware, but I mean this actually I want to acknowledge the limitation here. This mostly is just based on the ransomware you have read training. Okay, but if the ransomware, for example, new variant, potentially they have slightly different things happen here or here, but it may not work. I need to acknowledge this. Okay, that means that you need to do a little more ransomware sample training here to make sure that the threshold really can catch all those the ransomware you want to defend against. So
you
this is
know
a limitation, I guess.
Super. Thank you for doing that. I think, the final question, interest of time, I think, what is your advice for students and postdocs who are listening here? Any perspective on LLMs-based detector for LLM-based ransomware detector? Do you see an opportunity to automate something to look at these behavioral patterns using LLMs, in future, or what are you looking at?
I guess this is really very debatable question, right? So today you can see the LLM very popular. People try to use that to do everything. Malware detection, ransomware detection, software analysis, everything. But the thing here is that you need to think about whether really LLM is good for this scenario, right? Potentially it may not, right? Because for some LLMs come from natural language processing, right? So if you have this type of language semantic this thing, for example, if I use LLM to do this XX, right? Mostly it's a bunch of 1, 0 text or IO, all those things it may not as good as traditional AI, right? I don't know. So I don't see it could. I mean, it works. I can tell that because we actually work a bit here. It works. It can use to detect ransomware with some sort of 90% detection or something like that. But I'm not sure whether it's good compared to traditional AI, deep learning, right? So it may not the best solution because I am also slower, right? They have big model, a lot of parameter, right? Compared to traditional AI, deep learning, it may have small model or even very lightweight. I mean, the detection rate may not better than the old solution, but the performance could be slow. I guess it may not be a good solution. I don't know. So that's something I
What
observed.
what are you worried about in terms of sophisticated ransomware
Hmm.
characteristics that was going to happen? Are you anything that you're looking at that, oh, we have, okay, it's all based on trained signature samples, what we are doing. But when we're looking at distributed environment, when the tax comes in a distributed setting, and do you have any thoughts on what you think would be considerable a sophisticated ransomware attack?
I think really depends on the exact ransomware variant we talk about, right? So the first thing is that I believe that first ransomware actually mostly is a malware, right? All those malware we do know that's very diverse, right? Any type of malware. So but ransomware rely on those things to hack into a system. So I think from the problem point of view, mostly it's a malware problem, I guess, right? It's not a ransomware problem actually. So and then specific for ransomware, as I said, right? So we have this daily recovery problem. And also I think today the ransomware have something called double extortion, triple extortion. That means that it's not just data, not just encrypt data. Actually, try to, for example, in the double extortion, they also said, "Oh, I also steal your data, and then if you don't pay me, I'm going to declare your data in a public website." That's bad, right? So this actually, from this, it's not just the current problem, right? There's some sort of other problem you need to think about. But I think from this point of view, it's more like a traditional malware, something like that. So, but it's very diverse. So it need a lot of thinking, design, whatever, or customize for different scenario. Yeah. So hopefully
Super.
I have
Yeah.
some answer to that.
Thank you. Thank you so much, Dr. Bo, for this
Sure.
fascinating presentation. I think you will receive a nice plaque from UND and from a nice letter from our dean on the contribution what you have done. And we are also doing annually. UND is a Carnegie R1 classification institution. We also have a CAE-R. And we are also doing a major IEEE cybersecurity conference in October. We did that last year. And I will send you some invitation. Maybe you could be one of those speakers for us and help us review some papers too. I will send some requests there. Yeah,
Sure.
we'll chat.
No problem.
Yeah, thank you so much for your time this morning. Hopefully, we can see sometime in some conference. Maybe you can visit to North Dakota.
Yeah, definitely. So yeah, hopefully we can talk more for any future cooperation between my lab and the center of
Yes. Yeah.
emission tab.
Thank you, Dr. Bo. Take care.
Thank you. Bye.